Welcome back, everybody, to episode 45 of the Quantum Science Seminar. We have today our third hot topic session, where we asked our audience, you guys, to tell us about your latest and greatest results. And we chose 3 great speakers for you today. As usual, we would like to have your questions. Please send us your questions to quantumscienceseminar@gmail.com or use the YouTube live chat at the right or at the bottom of the screen. You should also notice that whenever you do so, that there is a 30-second time delay between what we do here and between what you see as live on YouTube. And with this, we will get started right away. Our very first speaker today is Maja Colautti from Florence, who will speak about integrated single molecule emitters. Please.
Can you hear me?
Yes.
Okay, so thanks for the presentation. I'm very happy for this great occasion. So today I will speak indeed of single organic molecules as quantum emitters, and I will try to convince you that these are excellent quantum systems, especially to address this ultimate vision, so this challenge that I depict here, so scaling up photonic quantum technologies. So since we're talking of quantum systems in the solid state, let's have a brief initial introduction. So probably the most common and known solid state quantum systems are for sure quantum dots and point defects in wide bandgap materials. They can ideally be represented as two-level systems, and they can be indeed excellent single photon sources, as well as excellent sensors in the nanoscale. In these slides, I will focus on photonics. And in general, solid-state quantum emitters can be potentially very convenient to scale up photonic experiments to multi-photon states, which are crucial not only for quantum networks, but also for boson sampling experiments and linear optical computing. In general, in order to effectively prepare multi-photon states, you need to fulfill some fundamental prerequisites. So you want your system to be scalable, so you want to be able to scale up to multiple emitters, and you want the single photon emission to be bright, so to have high rates, and fundamentally you want the differently emitted photons to be coherent and indistinguishable among each other. And this is crucial to perform two-photon quantum interference, which is key to many quantum quantum operations. So while a fundamental advantage of solid-state quantum emitters is that they can be easily coupled and integrated to photonic structures, one disadvantage is that you have to deal with the coherence effects, and that your emitters can also emit slightly different in frequency, and this is detrimental if you have to indeed convey indistinguishable photons for these applications. And specifically, I will talk about this at the end of the talk. So let's now talk about a rather unconventional emitter in the solid state, which is indeed organic molecules. So what is so special about them? Focusing on the family of polyaromatic hydrocarbons, once you can protect your molecules, your fluorophores in a crystalline matrix, you can really achieve photostable emission also at room temperature. Then there are really a wide availability of emission wavelengths. And secondly, for performing single molecule fluorescence microscopy, this setup is relatively simple. So our setup can really be summarized in a confocal microscope. So with the same objective, we excite and collect fluorescence, and with a set of filters to effectively take rid of the laser background. Most importantly, organic molecules are really easy and fast to fabricate, easy to handle, and this is the great advantage compared to other quantum systems. So let's go more in detail into our system. We work with the benzotyrrolene molecules into an anthracene matrix. And here you can see a typical sample we work with. So we can fabricate it really in 1 hour time. And these are submicrometric crystals of anthracene with DBT molecules inside. We can control them just to have one single DBT into each crystal. And this is very convenient, and I will talk about this later. If we look at the energetic scheme, it's a bit more complex than one of an atom. There are vibrational levels involved, several transitions, but the transition we focus on is the 0-0 phonon line. So this red line from the fundamental excited state to the fundamental ground state. When we cool the system to cryogenic temperature, this transition contains half of the overall emission. And indeed, we can really suppress coupling to phonons. In general, the quantum yield of the system is very good, it's almost unitary. So now let's look at the typical characterization that we can perform in our lab. Here you can see the anti-bunching dip. So this is really the fingerprint of single photon emission. We measure it by counting the coincidences at 2 detectors after a beam splitter. And this dip at 0 time is really attests for a low multi-photon probability, so a high purity of the source. Then we can look at the photon flux as a function of excitation power, and you can see that at maximum we can go above 1 million of single photons per second. And this is within this transition. And then if we can see the line width of this transition with excitation spectroscopy, and you can see that it's very narrow, so just few tens of megahertz. And this is, for this system, a Fourier limited value. So it means that it's very little affected by decoherence. And this is crucial indeed to perform two-photon quantum interference. So these are the results of a very recently accepted published paper. And we are performing here a Hongo-Mandel experiment with the photons from a single individual molecule. So if we have 2 impinging photons on the 2 inputs of a beam splitter, and these are prepared in the same quantum state, so they are indistinguishable, they will undergo coalescence. They will exit always at the same output. So because of essentially a destructive quantum interference effect, these probabilities are suppressed. Here we are also looking at the coincidences at the 2 detectors. And first, let's focus at the red data. So also here, we can see a dip at 0 delay time. It looks different because we're using here differently from before excited pulsed excitation. And this dip is indeed motivated by the suppression of coincidences due to coalescence. Then if we can compare this data with the blue ones, which are the ones for distinguishable photons that we can make by controlling the relative polarization and making it orthogonal. So the visibility of this quantum interference experiment can be calculated by comparing the areas of the central peaks, and we can evaluate an 80% value. Even more interesting, we could evaluate the residual dephasing and calculate that this visibility could go up to 96% if we could buy essentially a better cryostat, so go even to lower temperatures. Another interesting fact about working in pulsed excitation, which is in general key to go to any logical quantum operation, is that we can easily evaluate the collection efficiency of the experiment by comparing the photon pulses to the laser pulses. And we could evaluate this is actually just few percent into the objective. And this is due to the fact that we're indeed working here with bare nanocrystals, bare sources, not exploiting any cavity effect, any nanophotonics effect. While this is crucial in order to shape the emission pattern and effectively manipulate the emission, especially when you have a low numerical aperture objective, like in our case. So the way we needed to go to is really to integrate our source into a photonic structure. And this is not trivial for organic molecules. So the way we did it is really, we developed an alternative and hybrid solution. So we could exploit indeed the flexibility of these nanocrystal emitters, because we could disperse them into a polymeric liquid material. And we could use this direct laser writing fabrication technique in order to write any 3D structure that we wanted with very high nanometric resolution. And this is done with a tightly focused high power laser. At the focus, the liquid material gets solid. So by really shifting the laser in 3D dimensions, you can obtain your photonic structures with the advantage that having the nanocrystals dispersed in the material, you can have directly integrated structures. And you can see here the scenario that we achieved. So we could realize these light collecting elements, solid micro lens with the nanocrystal embedded at the base, which redirects fluorescence towards narrower angles, towards the objective, and a suspended waveguide with a nanocrystal at the central point, which funnels fluorescence towards convenient output modes. And now let's see how this integrated microlens can help in improving collection efficiency with our objective. So here you can see the SEM image of the final integrated structure with the nanocrystal at the base. And this is the backfocal plane measurement. So it's a fluorescence map in the momentum space. It's measured from the top of the structure, and it demonstrates that the effective redirection of fluorescence towards narrow angles. And here you can compare the saturation curves for the bare nanocrystal on glass with the nanocrystal integrated in the microlens. Looking at the maximum detected counts, you can see that we could really have a great improvement and reach 2.5 million single photons per second. We could also evaluate an increase in collection efficiency at the objective up to 40%. So this demonstrated that this hybrid strategy exploiting direct laser writing was indeed successful and promising. And now, as really last topic of these slides, I will talk about the possibilities indeed of scaling up to multi-photon experiments. So the main challenge here is that indeed, since we're working in the solid state, if you look at our single molecules in the matrix, they will actually feel a slightly different local interaction with the matrix due to the effects, to strain, and this has a consequence that the emission of different molecules can be slightly different, an effect called inhomogeneous broadening. So the typical way to solve this issue in order to go to indistinguishable emission for multi-photon states is using stark tuning via gold electrodes. But electrodes compared to the single emitters are rather macroscopic, so it's really hard to independently tune them, applying the suitable electric field. So what we discovered recently, together with the University of Leiden, is that we can actually perform on such organic molecular emitters an alternative frequency tuning method. And this is performed just by focusing tightly a pump laser on our nanocrystals. And indeed, we realized that we could observe a shift into at the transition line. And this is totally fabrication free, so it doesn't need for any preliminary step. And since it's an effect confined to the laser beam dimension, it's also micro-resolved and it can enable for independent tuning. So here I briefly show more in detail a typical measurement. So on the y-axis, you can see the time exposure to the pump laser, and on the x-axis, the frequency. These dark spots are indeed our transition line that is shifted. And you can also see that the linewidth is still very narrow, and this demonstrates that the effect is not heating induced. Also, I can tell you that this shift was always observed towards larger wavelengths, and this is actually compatible to the quadratic Stark effect typical of DBTSE systems. So our interpretation of this phenomenon is that we are activating a very local Stark effect due to a local build-up of an electric field. And this is laser induced, so after the exposure to the pump. And it's originated after a photoionization cascade and the formation of charge-separated states. The special thing of the effect is that these charge-separated states are long-lived, so the shift actually persists for hours, even after the pump is switched off. So we could exploit this tool to tune 5 different emitters in 5 nanocrystals. You can see them here in the spatial map. And you can compare here the transitions at the initially, so in dashed lines, they were more than 20 gigahertz apart, with the final transitions in solid lines. So we could really put them together into resonance within 2 line widths. And here I briefly show these 2 videos. So the time is actually the frequency of a tunable laser. When the laser matches the molecules, they light up. So I do it manually because it might be different to see them. But in this case, so this is a space map of fluorescence. You can see a single spot like this one appearing in different times, so different frequencies. And okay, like here, and there may be difficult to see. By the way, this was before the independent tuning process, while, after the tuning process, you can see them appearing really at the same time. So this is definitely a method that needs for optimization, but is a promising approach indeed to scale up to multi-photon experiments. So with this, I conclude. I have explained to you the photophysical properties of our emitter, and also I've shown this 3D integration method, which enables to enhance also the collection efficiency. And with this last optical frequency tuning method, I hope that I have convinced you that single molecules are indeed reliable, versatile, and also easy to use quantum emitters. And if you're yet not convinced, have a look at this. It will exit soon, this review on molecules. So our next steps are really to progress on multiple emitters experiment. As well, we want to focus also on secure communication, so to perform quantum key distribution experiments with our molecular photons. So thanks to my group, the collaborators, and here you can find the infos if you're interested in PhD or postdoc position, and thank you for the attention.
Thank you very much, Maja, for this beautiful talk. Very nice slides. There are several questions. The first one is actually by Bill Phillips, and he's asking, concerning brightness, I would have expected a molecule to pump into a dark state after a few emissions. Why doesn't it?
Yes, so actually for our specific system, oops, I wanted to change right. This so the probability for the passage to dark states is really, really low, like 10 to the minus 5, 6. So and this is also due to the very suitable combination of the emitter and of the matrix. Actually, yeah, to be this is just a very detailed. So in this saturation curve, you can actually see that here it drops down, and we're actually studying this effect. It's the first time that it's observed in our system, and it might be due indeed to a shelving effect, so from the excited state, but this is a detail. In general, the probability to dark states is really, really low.
Okay. Then there is another question, which is, do molecules bleach? And, and related to that, how long can you work with the same molecule?
Yeah, so actually they don't bleach and they don't blink. And this is, we can really work well at room temperature also for several days, at cryogenic temperature really for long times, ideally forever. And this is because at room temperature, the anthracene matrix sublimates, but we can also protect it, for example, with a polymer film. I mean, there are several strategies. So in general, no, blinking and photobleaching is not a problem. And this is due, again, to the combination of the fluorophore and the matrix. So the molecules can be protected in this way from oxidation and other deterioration effects.
Thank you very much. Then another one. So how do you prepare these nanocrystals with a single molecule?
Yeah, essentially, simply the fabrication is really mixing solutions, the solution of the matrix and the molecule, more or less. And then with this solution in water, you go for a reprecipitation method that can lead to aggregation in this submicrometric crystal. By controlling essentially the initial amount and portion between these matrix and fluorophore solutions, you can control the the average of the number of molecules in each crystal.
And a bit related to this question, would it be interesting to have many molecules in the same nanocrystal?
Yeah, for several reasons. Indeed, actually, one of our next goals, so next really interest is studying cooperative effects between multiple nearby molecules in the same nanocrystal, so nearby in frequency. And then in general, for example, it is useful to make test experiments. So if you want really to observe the result, for example, of integration exploiting a bigger amount of molecules, but yes, but let's say in general, you want to go for the single emitter level for quantum application for single photon states and multiple single photon states.
All right, thank you very much, Maja, once more for your talk. And now I'll give the mic to Sebastian to introduce the next speaker.
Yeah, thank you very much for a cool talk. Let's switch right away to our next speaker, which will be who will be Tom Darras from Paris, who will speak about entanglement in quantum networks. So please go right ahead.
Thank you, Sebastian. Thank you very much for the introduction. I'm very happy to be here today. So my name is Tom Darras. I'm a PhD student working in Laboratoire Kastler, Brossel, under the supervision of Julien Laura. And today I would like to talk to you about our work on optical hybrid entanglement and its application in heterogeneous quantum networks. So first, when we talk about quantum network, we refer to architectures that are composed of quantum nodes where you store and process the quantum information. And these quantum nodes, they are linked together via entanglement. And these quantum networks, they appear very interesting because they are thought to outperform classical information processing. For example, you can use quantum networks to access remotely and securely some quantum computers. You can also perform ultra-secure quantum cryptography in these quantum networks. And you can also enhance the measurement of physical constants using entanglement in the quantum networks. But yes, yet, as you know, these quantum networks, they are not yet available at large scale. And the reason for that is that you have two key ingredients you need to tackle experimentally. So our team at LKB, the quantum networks team, is pursuing an effort in both these directions. So the first thing you need if you want to create this quantum network is the ability to create quantum memories. So you can perform this by, for example, coupling a single photon to an atomic cloud, either in free space or as a vicinity of nano waveguide. And we demonstrated recently that using this system, you can achieve memory efficiency close to 90%, which makes them very promising for future quantum networks. So these experiments, they are very interesting, but this is not what I want to focus about today. Today, I want to focus on the second key ingredient for quantum networks, which is the ability to distribute entanglement in the channel and connect disparate quantum nodes. But before talking about entanglement, let's have a look at how we encode quantum information. And actually, historically, there have been two ways to encode quantum information. So the first one most of the people are familiar with is called the discrete variable encoding, where here you use a quantum system that belongs to a finite dimensional Hilbert space that we typically call qubit. And in the optical domain, you can, for example, encode a qubit in a superposition of vacuum entangled photons. These optical states, you can measure them using discrete variable tools such as single photon detectors, and you can characterize them using a discrete variable formalism that is the density matrix. But you have also another way to encode quantum information that has emerged that is called a continuous variable encoding, where here you use quantum states that belong to an infinite dimensional Hilbert space. And in the optical domain, you can use what we call optical Schrödinger-Cat states that are coherent superposition of coherent states with different phases. Then again, this continuous variable state, you can use specific continuous variable experimental tools to measure them, and you can also represent them using a phase-based representation such as the Wigner function. So these two ways to encode quantum information, they have actually been used separately in different protocols, and each of them has its own advantage and drawbacks. For example, if you look at the discrete variable encoding, you can generate and manipulate very efficiently this quantum state. But the problem of the protocols you implement using this state is that they are probabilistic, and so they are very hard to extend to large scale. On the other hand, using continuous variable state, you can implement some deterministic protocols. But the problem of this state is that they are very sensitive to transmission in a quantum channel. So for example, phase noise or transmission losses. And so as you can see, these two encodings, they actually have advantages that are compatible one with the other. And a strategy that now different labs are developing is, well, try to combine the tools from the two encoding to try to get the advantage of both. And a simplistic example you can think about is, well, why couldn't I use a homodyne detection, which is a very efficient measurement technique, which is phase sensitive on top, to measure a discrete variable state, and you can as well define, for example, the linear function of a single photon. And if you look in the context of quantum networks, well, the prospective quantum networks will, by essence, be composed of discrete variable nodes and continuous variable nodes, depending on the task at hand or the physical platform you want to couple with. But still, these quantum nodes, they need to be able to transfer their quantum information from one encoding to the other. And this the building block, if you want to achieve this, is to create what we call hybrid entanglement between discrete variable and continuous variable optical qubit. All right, so here is the outline of the presentation. So first, I want to give you an overview of the experimental tools we have in our lab at LKB to create these non-Gaussian quantum states, and how by combining these tools we can create the hybrid entanglement of light. And finally, I want to present the latest results we have published using hybrid entanglement as a resource in itself for quantum information processing protocols. Okay. So before talking about hybrid entanglement, we need to know how we can create the discrete variable and the continuous variable state separately. So for the discrete variable state generation, in our lab, we use optical parametric oscillators that are composed of a nonlinear crystal that is placed in an optical cavity to enhance the nonlinear interaction. If you want to create discrete variable state, you will use a type 2 phase match crystal, which gives you a type 2 phase match OPO. And if you pump this OPO far below threshold, you will see the emission of pairs of photons entangled in polarization. Then what you do is that you split these two photons on a polarizing beam splitter, and you send one of the two on a single photon detector. So in our case, the single photon detector we have in our lab at LKB, a superconducting nanowire single photon detector that present a record quantum efficiency above 90% at our working wavelengths in a very low dark energy. And then the idea is, well, when you detect a single photon on this detector, so what we call a click, you can herald the presence of the photon on this part of the experiment. And this state you can characterize very efficiently using homodyne detection. And so by using this protocol, we can create high purity single photon Fock state, with, as you can see here, a heralding efficiency, so which is equivalent to a collection efficiency, as Maja just presented earlier, around 90%. These states, we can create them at a heralding rate typically of a few hundred kilohertz. These states, since they have a very high purity, we can also now use them in more sophisticated protocol as the one I'm going to present today. And also, very recently, we have studied the capability of these heralded single photon to follow multi-photon interference. And we have demonstrated that if in an ideal scenario, you had 14 copies of such a state, you could, in an extreme bunching event, create a Fock state up to the number state 14. All right, so now we have all we need for the discrete variable state generation. We can create very high purity single photon. Now we can move to the continuous variable side. So for the continuous variable side, the setup is very similar, except that instead of having a type 2 OPO, we have a type 1 OPO, at the output of which you have squeeze vacuum. And in our operating regime with 3 dB of squeezing, this squeeze vacuum has a very large fidelity with an even cat state of an amplitude alpha square around 1. And then what we do very similarly, we tap a bit of the light, typically 1 photon, that we send to a single photon detector. And when you have a click on this single photon detector, we subtract 1 photon from the even cat state, and we have an odd cat state that we again characterize using homodyne detection. And by using this protocol, we can create again a high purity odd kitten state with an amplitude alpha square around 1. All right, so now we know how to create a DV state and a CV state, and now we want to create entanglement between the two. And to do that, the idea is to combine the two heralding paths in an indistinguishable fashion, so that when we have a click on an SNSPD, we cannot tell if the photon came from the type 2 or the type 1 OPO. And then you have two possibilities. Either the photon actually came from the type 2 OPO, which means on this part of the experiment, you have a single photon, and here you have an even cat state. Or the other possibility that is fully indistinguishable is that the photon actually came from the type 1 OPO, which means here you have an odd cat state, and here you have vacuum. And so you can understand how by using this protocol, we can create a hybrid entangled state between a discrete variable mode A here and a continuous variable mode here B. So I won't go into detail. You have the reference here if you are interested, but these states, of course, we can measure it experimentally using our high efficiency homodyne detection by performing two-mode quantum state tomography. And we can quantify the amount of entanglement in this system. So as you can see, this work, it has been done in our lab for several years. And now the strategy we have developed is engineering this hybrid entanglement and use it as a resource in itself to perform some quantum information processing protocol. And the protocol I want to talk to you about today is an entanglement swapping protocol. So as a reminder, what is entanglement swapping? Well, the idea is that you start from two independent entangled states. So here we have a single photon entanglement that we label dv-dv, and here we have a hybrid entanglement I just presented before. Then what you do is that you perform a specific measurement that is called the Bell state measurement between the two dv modes. And when this Bell state measurement, you create via teleportation a new hybrid entangled state between two modes that have never interacted. And so you can understand how this protocol can be used to connect disparate nodes on a quantum network that can be based on different encoding, and it can allow the distribution of hybrid entanglement in a network. So now the question you wonder is how we perform this protocol in the lab. Well, here is the experimental setup. So the idea is that we use the same two OPOs at different times to create first the dv-dv entanglement and then the hybrid entanglement. So first, at the times that I call T1, we use only the type 2 OPO with a heralding on SNSPD alpha to create a single photon here. This single photon, we send it for 50-50 beam splitter to create a single photon entanglement between mode A and B. Then at a later time that I call T2, we use the two OPOs conjointly with a click on SNSPD beta to create the hybrid entangled state I presented earlier. Then what we do, we mix mode B and C on a 50-50 beam splitter, and we perform the Bell state measurement here. So in our case, we implemented a hybrid Bell state measurement that is combining photon counting on SNSPD and quadrature conditioning on homodyne detection. So then, upon triple coincidental events between the three SNSPD, which occurs typically at a rate of 3 events per minute, we get a new hybrid entangled state between two modes that have never interacted. Of course, we need to accumulate enough data to reconstruct the state. So we repeat the experiment for about 8,000 quadratures. So if you do the calculation, it takes about 45 hours with an active feedback on all the phases involved. And upon two-mode quantum state tomography, we can reconstruct the two-mode state. So this is the density, the two-mode density matrix of the state. And what we are interested in here are the coherence terms, so the anti-diagonal terms that are characteristic of the entanglement. So here we can see the appearance of these anti-diagonal terms that are also present in the Wigner function of the projection of the two-mode density matrix. And this is to be compared to what you would get without performing the Bell state measurement here. So you can see that you have no coherences, so no entanglement. Of course, and if you are interested, you have the reference here. We did in the paper a detailed statistical analysis to prove that we have indeed entanglement after swapping. So a final thing I want to mention is, well, if you think about hybrid entanglement swapping in the context of heterogeneous network, in terms of propagation of entanglement, swapping should be better to what you would get at some point by directly propagating your entanglement in your network, because your quantum nodes will, of course, be lossy, and your entanglement will be lost. So here we compare theoretically the evolution of the hybrid, so the negativity of the hybrid entanglement as a function of a distance. So here in blue, we show what we have by directly propagating hybrid entanglement. So here you see an exponential decrease of the negativity of entanglement F with the distance. But here, if we perform swapping, we see that after a given distance, which if you take optical fibers at telecom, you could beat direct propagation by performing swapping after a distance of a few tens of kilometers. Of course, your protocol will be limited in the end by the dark count in your detectors, but this is only a technological limitation that can be improved in the future. And of course, you see that with propagation, you always lose entanglement. So you need after propagation to apply some active protocols and purify your entanglement at the level of the quantum nodes. All right, so to summarize what I've presented to you today. So first, we have seen what are the experimental tools we have in our lab at LKB to perform optical quantum state engineering, and how by combining these tools, we can create the hybrid entanglement between discrete and continuous variable optical qubits. And finally, how we can use this hybrid entanglement as a resource in itself in quantum information processing protocols. Here are the people that were involved in this work. And with that, I would like to thank you for your attention. And if you have any question, I would be more than happy to answer. Thank you.
Thank you very much, Tom, for the nice talk. We have several questions. There are some regarding the encoding of the information with the two possibilities, discrete or continuous variables. The first one is regarding the encoding in the continuous variables. Is it correct that you encode the qubit in the two possible states of the Schrödinger cat state, alpha and minus alpha, or is it on the phase of such?
So you can you encode in both. So you have a super. You can see your CV basis as a qubit basis, where your 0 will be your alpha and your 1 will be your minus alpha. So then you can encode anything in any superposition of alpha and minus alpha with the phase you want.
And since this is related, then the digitalness of such a cat state, is it determined by the amplitude of the source of the coherent state compared to its quantum noise? Because of course the two states are not orthogonal.
Yeah, so the idea is that of course you want to have the cat as large as possible. So that's a goal we are performing, but when you are working with optical parametric oscillator, you are limited by the cat of the size you want to create. So if you want to enlarge, for example, your basis to have orthogonal coherent states, you will need to push more your pump power and your OPO, but when you do that, you decrease the purity of the state you generate. So overall, you cannot reach the largest value of alpha we reach experimentally in our lab were about alpha square around 3 using another protocol involving a type 2 OPO. But if you use other platforms such as superconducting circuits, you can achieve much larger cats.
And regarding the encoding of information in the discrete state, you mentioned the possibility to encode into the 0+1 Fock state, which is a state that would be sensitive to photon loss. But how would this compare to encoding in the polarization, in the two polarization states of a photon?
Yeah, so it's exactly the route we are following in our lab at LKB is to move from this Fock basis encoding of the DV mode to a polarization encoding. Because in our case, we are very sensitive to the loss of photon, which correspond to a bit flip. So we would like in the future to extend the hybrid entanglement to polarization qubit. But if you want to do that, you need to increase the number of photons involved in your experiment. So we increased very recently the capability of our experiment by adding a second type 2 OPO. And by using the two type 2 OPOs together, you can create a polarization, entangled polarization source, and from that create the hybrid entanglement. So this is a route we are following in our lab.
And there is a question from Bill Phillips, again, related to the encoding of information in the continuous variables case. So since the two coherent states are not mutually orthogonal, does this impose a fundamental limit on the fidelity of some operations? And does it matter?
Yeah, it actually imposes some limitation, but it depends on the protocol you want to use. So for example, if you want, let's say you imagine similarly a teleportation scheme, if you want to apply an active feedback on your state to teleport it in the CV basis, this operation, so moving from the even to odd cat state by applying a displacement, is only true if you have a very large size of alpha. So for example, with our state we have right now, we cannot apply an active feedback if we wanted to perform some deterministic teleportation.
Thank you. And then a broad question. So clearly each of discrete and continuous variables have their own advantages and disadvantages. How can you make sure you avoid combining the disadvantages in the hybrid case? For example, in the hybrid case, how can we avoid the downside you mentioned that continuous variables encodings are sensitive to perturbations?
Well, we are not really, in our case, avoiding the limitation, because if you look at the entanglement swapping we perform, we are actually, by heralding, imposing a probabilistic protocol on a continuous variable state. But this again, you could, for example, you can couple this heralding with the memory to increase the rate. So, for example, in our case, the fact that we perform a DV-like teleportation scheme is giving a limitation to the continuous variable bond. So you need to find smart protocols where you can win a bit on both. But for example, in our case, we can win in terms of fidelity and connection, but we are losing in terms of rate.
Okay, thank you very much, Tom, once more for your talk. I'll pass the mic now to Sebastian.
Yeah, thank you also very much from my side. That brings us to our final speaker today, who is Daniel Gonçalves Romeo from Barcelona, who will speak about Rydberg atom arrays. So Daniel, please go right ahead.
Yeah, thanks, Sebastian. Let me prepare everything. So hi everyone. I would like to start thanking the organizers for giving us the opportunity to share some of our results here at the Quantum Science Seminar. In this project, we explore the combination of ordered atomic arrays with Rydberg interactions as a promising platform for quantum nonlinear optics. This work has been done in collaboration with Dr. Mariona Moreno Cardoné from Universitat de Barcelona, and in collaboration with Professor Tariq Sang, who is my thesis advisor at ICFO. To motivate my talk, I would like to start with a very broad statement, which is that photons do not interact with each other in free space. This makes them good candidates to carry quantum information, but it makes the processing of this information rather difficult. Therefore, at the end of the day, one needs platforms that mediate the interactions between photons. And perhaps one of the most promising systems to achieve such tasks are systems that exhibit quantum nonlinear optics. So I will start with perhaps the simplest example of a nonlinear medium, and that would be an ideal two-level atom. Since a two-level atom cannot be excited twice by resonant light, if I shine two photons at the same time, I can basically saturate the optical response of this system. However, what happens in real experiments is that these two photons basically propagate through the system without interacting. The reason for that is that the atom-light coupling in free space is actually very weak, and the interaction probability scales with the wavelength squared divided by the cross-section area of this beam. Therefore, the diffraction limit prevents us from getting this strong atom-light coupling. One way to solve this is just increasing the number of targets. By doing so, now the interaction probability scales with the number of illuminated atoms. However, notice that here, although we're increasing this coupling efficiency, the nonlinearity is actually very low, because in order to have a nonlinear event, I will need that two photons scatter the same atom at the same time. And this is rather difficult given the typical size of these photonic wave packets and the fact that you have multiple atoms. Perhaps the most promising approach to realize quantum nonlinear optics in atomic ensembles has been this Rydberg electromagnetic induced transparency approach. In a standard TIT, you have an atomic ensemble of three-level atoms with ground, excited, and Rydberg states. You have a coherent control field that couples this excited to Rydberg transition, and you are interested in the propagation of photons in the ground to excited transition. Roughly, the general idea is that these photons will propagate through the system hybridizing with a Rydberg excitation, in such a way that by satisfying an EIT resonance condition, these photons will propagate as if the system is completely transparent. The interesting thing about Rydberg EIT is the fact that these photons are hybridizing with Rydberg states. Rydberg states are atomic states that have a very large principal quantum number, which means that they will have a very large dipole moment. Therefore, one can expect strong dipole-dipole interactions within Rydberg states, and this gives rise to something called the blockade effect. Mainly, this is an effect that prevents two atoms to be simultaneously excited to the Rydberg state if they are closer than a distance RV. So you can imagine if I now shine two photons through this system, and they are closer than this blockade radius, there will happen this blockade effect. So basically, the first photon hybridizes with a Rydberg state and sees a transparent medium, but the second photon sees all the energy levels shifted because of this dipole-dipole interaction. And in this case, the resonance EIT condition is broken, and instead of a transparent medium, gets scattered into random directions. So we see that by introducing Rydberg interactions, now the system becomes very nonlinear, because just with a single photon, I can modify the optical response of a macroscopic region involving several atoms. However, we know that this nonlinearity is very dissipative. This reduces the efficiency of implementations such as photon-photon gates, in which the error scaling goes as the blockade radius to the -3 halves. The typical values for the photon loss is around 90% for 2 photons. So this means that if I shine 2 photons into these gates, less than 10% of the times, I will be able to recover these 2 photons in the state that I want them to be in. So what we do in this project, we try to solve this dissipative nature of this ensemble by exploiting the properties of ordered atomic media. So in the rest of this talk, I will combine 2 main physical ideas. The first idea is that a 2-dimensional array of atoms can behave as a perfect mirror. And the second idea is that by introducing Rydberg excitations, I can create apertures into this mirror. Okay, so for the first part, I will give you some intuitive ideas on why this array should behave as a mirror. So for now, consider an infinite 2-dimensional array of 2-level atoms, and I shine a specific plane wave with a certain k vector. Due to the spatial ordering of these atoms, light can only be scattered in specific directions, which I symbolize by these green arrows. This is similar to what happens in Bragg diffraction, in which interference phenomena defines well-defined diffraction orders. Importantly, if I now consider that the distance between the atoms is smaller than the wavelength that I am using, so basically have a sub-lattice lattice constant, so wavelength lattice constant, most of these directions actually become evanescent, in such a way that light cannot leave the system in either the reflected or transmitted mode. On top of this, if now I shine light on resonance, I get total destructive interference in transmission, in such a way that now light can only be reflected into a single mode. This is what I define as perfect reflection, a situation in which you have 100% interaction probability and reflection back into a single mode. This means that the photon is not reflected into an arbitrary direction. Of course, this is an idealized system, but even if you consider a finite size system with a Gaussian beam illuminating this system, you get values for reflection that are higher than 95% for numerical simulations. The performance of this mirror will actually depend on the ratio between the area that you're illuminating and the size of the mirror. So you can imagine that if your beam waist is very large, basically the light will leak through the edges of this mirror. And if you focus a lot your beam, then this mirror approximation basically breaks down because it's a collective effect and you need to illuminate several atoms. Therefore, there will exist an optimal beam waist between these 2 regimes that maximizes reflection. So at the beginning of the talk, we discussed that it was important to have nonlinear systems to mediate this interaction between photons. So now we wonder how much nonlinear is this mirror. In order to quantify the nonlinearity, we're going to introduce the second-order correlation function, which formally is a parameter that measures the likelihood of measuring 2 photons in reflection. But for us, we'll quantify the effect of reflecting one. So quantifies the effect that reflecting 1 photon has in the reflection of a second photon. So imagine this scenario. We have our mirror array and we send 2 photons. If this G2 is equal to 1, it means that the mirror has a linear behavior. So this means that the reflection of 1 photon does not affect the reflection of a subsequent photon, or basically that 1 photon doesn't affect the other one. And if this G2 is smaller than 1, we have a nonlinear behavior. Notice that the only nonlinear phenomena that can happen here is a situation in which 2 photons scatter the same atom at the same time. In that situation, 1 photon will excite one of the atoms. And since a 2-level atom cannot be excited twice, this will create a single atom aperture in my mirror that will reduce the probability of reflection for a subsequent photon. This effect can be seen in the second-order correlation function. So here I'm plotting how much does this G2 deviate from unity as a function of the illuminated atoms. If I illuminate very few number of atoms, you can see that the fact that there is 1 atom missing matters a lot, which makes sense. However, the more atoms I illuminate, the less relevant is this atom missing, and therefore what this does is washes out the nonlinearity. So you can see that we find somehow a dilemma here, because we want to illuminate a large number of atoms in order to have this very interesting mirror behavior. But at the same time, if we do so, we wash out the nonlinearity of the system. So now we wonder if there is a way to increase the nonlinearity of this system, and the answer is yes. We're going to do that by increasing the size of this aperture. So we go from a single atom hole into a hole that has the size of the blockade radius. And we do that by using Rydberg interactions. We will exploit this blockade mechanism that we saw before. Basically, we do a two-step process. First, we store a Rydberg excitation in the system by means of a coherent control field that couples this excited to Rydberg transition. So what happens is when one photon comes, this excites one atom, and then by means of this coherent field, I complete a two-photon process towards the Rydberg state. So now I have Rydberg excitation in my system. So the next step will consist on detuning this control field. This is a slightly different approach from the standard Rydberg EIT. And what happens here is that this control field will dress the excited states, introducing an energy shift that is proportional to 1 over the detuning. Interestingly, the presence of a Rydberg interaction will basically modify this dressing, giving rise to a dressing-induced interaction potential. The idea is that by using this control field, we can communicate this blockade mechanism that happens in the Rydberg states to the excited states. Here I'm plotting the shape of this dressing-induced interaction potential as a function of the distance between one excited atom and the Rydberg excitation that we have previously stored. So in some sense, what you can see here is that if these atoms are very close to the Rydberg excitation, this will be very shifted out of resonance. Otherwise, if they are far away, they will not be shifted at all. So if I now shine resonant light, what will happen is that the atoms within the blockade region will be out of resonance in such a way that now they behave as a transparent region. So what I'm creating is just an aperture into this mirror that has the size of the blockade radius. So finally, what I will do is I will combine these two physical ideas to basically implement a single photon switch. We will consider two main scenarios, one reflecting a scenario in which we have all the atoms in the ground state, and a transmitting a scenario in which we also have all the atoms in the ground state, but now we store a gate photon. So basically we have all in the ground state, and now a Rydberg excitation is stored here. So now we detune the coherent control field to work in this Rydberg dressing scenario, and then we send a signal photon. In this case, by choosing properly the frequency of the signal photon, we can get this perfect reflection that we discussed before. So this photon will be reflected into a single mode. On the other hand, in this transmitting scenario, these dressing-induced interactions will create an aperture that will allow the transmission of a signal photon. So overall, what we are doing here is we are conditioning the transmission and reflection of a signal photon as a function of the storage of a gate photon. So by storing a gate photon, we can switch between transmission and reflection. One of the questions we had was, how can one optimize this system and which will be the best performance that it can achieve? And for that, we solve an optimization problem that I will describe from the perspective of the beam width. So before we saw that if my beam width is very large, basically light can leak through the edges of the array. On the other hand, if this beam width is very small, then this mirror behavior is broken because this is a collective effect and I need to illuminate several atoms. On top of this, we now add an additional constraint, which is that we want that our photons coincide with the aperture in the transmission scenario. So by solving this type of optimization problems, we managed to find basically the optimal gate error as a function of the blockade radius. This error is basically the maximal error between transmission and reflection scenarios, because we want something that works well in both scenarios. And this can be seen as the probability that the gate does not work as intended, including photon loss. This value we derived with a toy model, and basically we obtain a scaling for this error that is the blockade radius to the -4. This, in principle, would outperform the best gate protocol that you have for disordered atomic ensembles. And on top of this, if we consider realistic values for this array size and these Rydberg dressing potentials, we predict that we can have a photon loss that is below 5% for both photons. So with this, I hope I managed to convince you that with this approach, it's possible to achieve strong and nonlinear photon-photon interactions with low dissipation. Thank you very much for your attention, and if you have questions, I will try to answer them.
Thank you very much, Daniel, for the nice talk. We have several questions.
Great.
So the first one is, in the 2D array as a perfect mirror, how does the reflectivity depend on the motional temperature of the atoms?
Yeah, sure. That's something important. In fact, there is a publication from Emmanuel Bloch's group in which they study this reflection problem, and actually thermal effects and this moving of the atoms is actually important. So in our case, we don't treat that specifically in our approach. We consider that the atoms are fixed in specific positions, but you can imagine that by using single photons, it's going to be hard to basically heat your system, basically. So your system should remain cool. But yeah, it's something that definitely has to be calculated in more detail.
Good. And another one, would it be possible to think of this potentially as a single photon transistor, where the presence of a single photon that interacts with the atoms and generates the Rydberg excitation can control the path of a single photon approaching the array?
Yes, yes. So it can be used as a transistor. I guess the definition of transistor is a little bit more complex. So I prefer saying it as a switch in this sense. Right, but yeah, definitely we can control the direction of photons using this array. Right now, we are only considering one direction, basically, either reflected or transmitted.
Mm-hmm. Good. Also, if one couples one atom to a waveguide or uses non-Gaussian electromagnetic field modes in free space, one can have, in principle, total reflection even with one atom. So could these ideas of using photonic strategies help in that context for 2D arrays?
Yes, so in that sense, you will have to work with the band structure of your system. So in our case, we use just classical optics, but perhaps exploring different array shapes, maybe one can find a band structure that actually gives you a better scaling for the reflection. However, we think that there are other possible experimental errors that would be more important than these effects that has to be addressed first. But yeah.
And related also to the question about temperature and having systems disordered, Bill Phillips is asking, how would things change if the atoms were not in a regular array, but in a disordered gas?
So the problem of a disordered gas is that then this mirror behavior is not as good. So basically, in order to have this perfect reflection that basically reflects your photons into specific directions and so on, so this control, you can manage to get it because the atoms are ordered. If you go to this disordered situation, then photons get scattered into random directions, which is what you have in the current proposed protocols.
And perhaps in that context, there is also the question, what is the conceptual difference between your proposed single photon switch and the previous experiments with unordered atoms in dipole traps by the Bulletich group?
So I'm not sure if I'm familiar with those experiments. What I would say is that, so can you repeat the question, sorry?
So what is the conceptual difference between your proposed single photon switch and the previous experiments with unordered atoms in dipole traps by the Bulletich?
Sure, yeah, I think now I recall. So basically, in our case, we are including this mechanism that creates the aperture within the array. So it's something that is built in everything in the array. And that I think that's the main difference compared to the Bulletich case, yeah.
And then general one, which would be the biggest experimental challenges in performing this experiment?
So overall, we are combining two things that have more or less already been proved. So there is Emmanuel Bloch group in which they work with this perfect array. And then we have experiments in which they work with these Rydberg excitations and blockade mechanisms. So in principle, everything we say more or less exists, but separated. So we want to combine these things, right? So from the case of the array, perhaps the main problems that can arise are the filling factor. So filling factor is going to be very important in order to have this perfect reflection. Also thermal effects, as we discussed before. And then for the case of the storing the Rydberg excitation, you also need that this excitation is basically maintained during the whole protocol, so you don't have any accidental retrieval or decay. And you have also to worry about, for instance, perturbations or radio frequency fields affecting your Rydberg excitation, microwave fields affecting your Rydberg excitation.
Good. Then the maybe last question by email from Tomas Sanchez Pastor. This approach, so the question is whether this approach can be used as a switch in a quantum computer.
Yes, although I'm not sure about, so yes, for sure. And actually our intention is to have these interactions that are coherent and are controllable in the sense that you don't have this probabilistic situation in which your gate works 10% of the time. So we want something that works deterministically most of the times, and certainly it would be useful for a quantum computer. The thing is that in order to scale this, it's going to be hard, right? You cannot have like several arrays to create several gates, but it's an approach that can be explored for sure.
All right. Thank you very much, Daniel, for answering all the questions and for your talk. I'll pass now the mic to Sebastian.
Yeah, thank you also again from my side, Daniel. And thanks to all our speakers today for keeping perfectly on time, which is why I have a minute to say a few words. So next week, we'll have yet another talk by Alexia Orfev, who will speak about quantum thermodynamics, yet another topic that we haven't covered. And you should certainly also check out our sister seminar, the virtual AMO seminar, where tomorrow they'll have David Weld speaking about localization and delocalization in kicked quantum matter. If you want to get notified about what we do, please go to our website, quantumscienceseminar.com. You can subscribe to our email list and you can look at our Google Calendar. You can follow us on Twitter as well. With that, I'd like to thank you for your interest and we hope to see you again next week, same time, same place. Bye.